So I hope you were able to solve week 2 assignment problems, right? Were there
Yes.
any?
Yeah.
Yeah. Yeah. So now I hope my screen is visible. So today actually I am a bit down with fever, so please bear with me if my sound is not proper.
It's okay, sir. Fine. It's not
Okay,
okay.
thanks.
Yeah. Yes.
So this is the first problem of this week. So here it is been asked that we have to calculate pitch factor for a 4-pole 36 slot winding. Okay, and pitch factor, you if you might have gone through the lectures, that pitch factor is nothing but cos
SVP.
alpha.
Alpha.
Yeah, and alpha is nothing but the slot angle by which you have sorted your slots. So if you have gone through the lecture, you might be knowing about distributed winding. And in distributed winding, you have two types of winding. Either you can have full pitch winding or you can have short pitch winding. Okay.
Yes, sir.
So the thing is with full pitch winding is that uh, you cover entire pole region on the slot. So and we go ahead with short pitch winding to eliminate certain harmonics. So it might not be clear. So let me open a software so that I can show you winding arrangement. Okay, just to make it a bit clear. I'll open my laptop.
You want to show it in MotorCAD, sir?
Right, right. I want to show in MotorCAD. Let me just present from my laptop so that. Okay, so I hope my screen is visible from my laptop. So you might see a winding arrangement on my screen, right?
Yes, sir.
Yeah. So the thing is that this combination is 24 slots and 4 poles. So this is a typical example of a permanent magnet synchronous motor. Okay, so this is the magnet that is placed on the rotor surface near the air gap. In between there is air gap, and this red member is our stator core. So this is a stator teeth, and this is a stator back iron. And here the yellow member is nothing but the armature
Slot.
winding. Where
Yellow
yeah,
one is slot, no? Okay, slot.
yeah,
Why?
in slot how the armature is placed. So let me show you how the armatures are placed. So this is your slot looks like, where multiple conductors are placed. So this you can assume as one conductor, right? So multiple conductors correspond to single turn. So if you want to maintain a turn, like let's say two conductors from the both sides, so kind of this. So just take for example, uh, you know, so yeah, so you can see that this conductor or this wire, this armature wire, is coming out of the 14th slot and it is going to the 19th slot, right? So
Yes.
one conductor in 19th and one conductor in 14th. So two conductor is corresponding to one turn, right? So that is what happens in one uh, one conductor, two conductors, how they contribute to make one turn. Okay.
Yes, sir.
And the important thing I wanted to show, in distributed winding. So see, this is the distributed winding. Why I am saying so? Uh, for concentrated winding, they would be, wound around the two.
Throw is one. And
Yeah, exactly. Throw is one. So see, this is how concentrated winding is made up of. right? So you can see it is coming out of 14 and it is going in 15. So it is wound around the tooth, right?
Yes,
But
sir.
when the throw is, slot per pole, so here the slot is 24 and pole is 4. So the throw should be 6 to have the full pitch winding. So this is how full pitch winding looks like. Okay.
Yes,
So
sir.
it is wound around the entire polar region. So if let us suppose that your pole is getting started from here, at the end of this magnet, it should end near the other polar region, right?
North Pole means it will starting at North Pole means it completed South Pole. Some like
Exactly. So electrically 180 degree it should
180 degree.
complete. Yeah. So this is how your winding looks like. If you want to see linear pattern, so this is how it is wound around the core, right? So it will, so see here, from the first conductor, from the first slot, this first conductor is going, right, and with this overhang it is coming in seventh. So it has traveled 6 slots. So that is what full pitch winding we mean by that, right?
Yes,
So
sir.
let's see here how are the harmonic factors. So if you want to see the harmonic, so this is the harmonic factor we tend to look. So fundamental harmonic amplitude is 0.96. So this is what? This is your winding factor, right? So winding factor is nothing but the multiplication of pitch factor into your winding factor lead to a multiplication of pitch factor into
Yes.
one other factor is there, right?
Slot factor कुछ.
Yeah, exactly,
Yes.
slot factor.
Slot
So
factor.
if you multiply both the factors, you will get the winding factor. So
Winding.
you can see that fundamental is close to 1, like it is high. 0.965 is considered as high winding factor. But you also have dominant third harmonics, that is 0.7, right? So you can see this third harmonics, right? Its magnitude is 0.707. So sometimes, and this harmonic will be reflected into air gap flux density if we are providing armature current to load the machine. So what happens, let's see, if you reduce your throw, you are sorting it by 1 slot. So now our throw should be 5. See? So I have reduced this throw value from 6 to 5. So I have sorted it. I have sorted my winding by 1 slot. So how does it look like now? So yeah, here you can see. So earlier it was getting ended, it was coming out of 14 and it was going into 19, right? Now it is going to 18. So one slot will be taken by some other stage or some other path or some other coil rather, right?
Yes.
So that's how this one slot is sorted. And you have to calculate the slot angle. How will you calculate one slot angle? So let's say we have 24 slots and entire
360 degrees.
entire mechanical degree is 360 degree, right?
Mm.
So and 1 by 24 into 360, that will correspond you to a mechanical angle, right? So 24
15
360
degrees
by
is the
20.
mechanical angle.
Yeah, exactly. So 15 degree will be mechanical angle. And how
P by
how
2
much?
into mechanical degree equal to electrical degree.
Exactly. So here 4 poles, so 30 degree will be your electrical degree.
Electrical
So
degree,
by
yes.
30 degree here we are sorting our armature slots. Okay, so and now let's see the impact on the winding factor, which is the very important. So see, we are doing such kind of winding just to utilize the maximum of our winding factor. So now let's see harmonics in the winding. So you can see here that fundamental is reduced from 0.96 to 0.93. On the other hand, third harmonic component is also reduced from 0.7 to 0.5. Yeah. So here reduction in third harmonics you can see. So if you want to eliminate any particular harmonics, you can calculate, cos n alpha by 2, or rather cos n alpha, which is alpha is nothing but the slot angle and n is harmonic, and equate that is equal to 180 degree. 180 or 90? Yeah,
180.
90. Multiple of 90. So cosine is 0 at multiple of 90, right?
Mm-hmm. Yes.
Yeah. So we have to do that, and then you will get to eliminate those particular harmonics. Okay, so we will see from the problems also that how to eliminate them. So let any doubt from this, any winding arrangement or something?
I have small harmonics, sir. How to read harmonics and like harmonics means unwanted that frequency, So how to?
Yeah, actually, see, when you are winding any machine, right? You are distributing it to just to get rid of distributed winding has lower harmonic content than concentrated winding.
Hmm.
Okay, because you are what does distribution mean? Distribution means you are distributing conductors sinusoidally along the periphery of the pole, right? Or in the slots. So by distribution, you are not loading any single tooth so that all the flux from the winding that will be earlier. So let's call it, all the flux is concentrated in one slot. Now here what is happening that all the flux corresponding to one pole is now not restricted to only one slot combination or only one tooth wind. It has been distributed along the periphery of the pole.
Yes.
So it's just a phenomena of distribution. So when we will be seeing the harmonic topic, we can discuss in detail. But just for now, keep in mind that distributed winding is leading to the distribution of winding MMF, so that we can get more sinusoidal. So I think here one linear pattern. Let me just show you. Yeah. So you can see here, right? So here the winding MMF, you can see winding MMF how they are being distributed. So this kind of waveform, so you are placing your conductor for this phase, right? So you're placing your conductor in 6th slot, then 7th slot, then 8th slot, right? And then you are coming back after distribution in one pole periphery. You are coming back to 12, 13, and 14. So this kind of waveform will lead you, if you do the Fourier analysis, this kind of waveform will lead to more sinusoidal component compared to your concentrated winding. So let me see whether I have concentrated winding example or not. Yeah, so this is fractional slot concentrated winding. We will learn about that also. 12 slots, 8 pole, right? So what will happen here? Yeah. So you compare both the waveforms. See here, it is just plus minus a square waveforms. So it is less tends to sinusoidal. If you compute the FFT, it has higher harmonics. So you see all the harmonics is close to same value,
Same
right?
value. Yes.
So and even fundamental is reduced to 0.86. On the other hand, in distributed we were getting up to 0.96. So even fundamental is reduced and other harmonic components are very high. So this is how your waveform distribution of winding will look like. So this is how in slot, if you are placing the conductor, then this is how your MMF waveforms will look like. On the other hand, for this distributed, the more you distribute, the more your waveform will be sinusoidal. That's what I mean to conclude here. Any other doubt?
No, sir. Please.
Okay, great. Great, you are asking those type of questions. So these harmonics are really necessary if you are going to design a machine, because harmonics can play a very high role, especially in high-speed machines, right?
Yes, sir.
Yeah. So let's get back to the problems. Yes. So here you can see that 4-pole 36 slot winding, right? So how much should be full pitch distribution? How much should be through?
త్రూ ఈజ్ 6. అర్థమవుతుంది. 8.
So for full pitch winding should be slot per pole, right?
Yes.
So slot is 36, pole is 4, so it will be 9,
9.
right? But in the problem, it has been mentioned that winding has a coil span of 1 to 8. Like it is coming out of
Short pitch.
first slot, yeah, and it is going to 8th. In between also multiple slots are there. So how much is the coil span? In terms of slot,
7.
can you let me know? 7.
8 minus 1, 7.
Yeah, so 7 is the coil span. For full pitch, it should have been 9.
9.
But it is right now 7. So it has been sorted by 2 slots. Right. So can you calculate the pitch factor? Pitch factor is cos alpha. Please let me know this value after calculation, okay?
The 0.342.
0.342. Let us see how much will this value be. So alpha will be 2 by 9, right? Into 180 degree. Why 180 degree? Because had it been full pitch winding, the alpha should have been 180 degree, right?
2 into 180 divided by 9. So 40.
So alpha will be 40 degree and cos alpha will be
0.76.
0.76. So this much is your pitch factor. So sorry, cos alpha by 2. This value is cos alpha by 2. Okay.
0.383. Cos alpha by 2 by 20 degrees cos 20.
0.38 is it coming? Let me calculate.
Actually, alpha by 2 means is 40 degrees is the alpha, so 20 degrees cos 20 is 0.939.
Exactly. So cos 20 is
0.939.
99. So see, so this will be a factor in pitch factor. So pitch factor should be ideally it should be higher than 0.9. So it seems to be correct. If you are getting pitch factor like very poor, then be
Very poor.
cautious, right? So
It's
generally
not
pitch
good.
factor, yeah. So generally pitch factor lies from 0.9 to 0.95, 0.96. Just now what I saw, right? So any doubt in this problem?
No, sir.
Okay, so let's move to the second problem. I hope you are able to see the second problem. It is a 6-pole star-connected 3-phase alternator driven at 1000 RPM, has 108 slots with 10 conductors per slot, right? The slot angle and number of turns per phase we have to calculate. So slot angle easily we can calculate, right? So we have 108 slots, right?
Yes, sir.
And a 6 pole. So for one pole, there will be how many slots? So let us see, 108 by
6.
6,
18.
18.
18, sir.
18 slots per pole, right?
Pole.
And that will correspond to 180 degrees, isn't it?
Yes, sir.
If consider that if you are going for full pitch winding, so 18 slots will lead to 180 degree and 180 degree electrical, right? Now we have to calculate slot angle. So 18 slots is equal to 180 degrees. So one slot will lead to 18 degree, right? And
18
it has,
slot to
yeah,
180
18,
degree.
yes, yes. So it has a standard equation also, that slot angle 180 degree divided by slot per pole. Either you can remember this or you can derive from yourself.
Sir, one slot equal to 18 degrees or 10 degrees, sir?
Yeah, 10 degree. Yeah, sorry, I'm wrong there. 10 degree. Right. So now the second part of this problem, how many number of turns per phase?
Okay, turns per phase. Already they given conductors, no Z. So there, from there
Yeah,
we can calculate, na, sir.
exactly.
One turn equal to conductors, sir.
One turn is equal to two
Two
conductors.
conductors, sir.
So 10 conductors for one slot. Okay.
One slots. Total how many slots? 108 slots.
And it will be equal to 5 turns.
5 turns.
Okay.
Yes, sir.
Now we have total 108 slots.
108 into 5. 108 into 5. 540.
108 slots will be equal to 5 times 108. That will
Yes.
be number of turns per conductor.
And that 108 slots turns, sir. 5 is a turns, no?
Right. That's why
Yes.
we are multiplying with 5 here.
5, yes. And
So
3 phase
total,
also by 3.
yeah, by 3. If you have 3 phase, then by 3.
By
So
3.
this 5 into 108 is equal to total number of turns, and that will be divided with 3 phase. So that will
180.
be total number of turns per phase.
180 turns, sir.
180 turns per phase.
180.
Any doubt in this problem?
No, sir. No, sir. Clear.
Okay, let us go ahead with the next problem. Okay. So kindly read this problem.
No questions, sir. We unable to see any questions over here.
So I hope you are able to read the problem. So
Now,
did you get any idea how to solve it? So a 4-pole, 25 horsepower, 500 volts, 600 RPM series motor. Efficiency is given. Pole faces are mentioned as a square. and ratio of pole arc to pole pitch is 0.67. Okay.
Mm.
Assuming an air gap flux density of 0.55 Weber per meter square, which is electric loading also, and ampere conductor per meter.
Is
So that
electric
yeah,
loading.
that is electric loading. So you are given with magnetic loading and electric loading,
Electric
right?
loading. Yes,
You
sir.
just need to calculate the bore diameter of the stator.
Later. They give an efficiency also.
Yeah, they have given efficiency. So equation of power in terms of diameter of the motor and length of the motor must have been derived in the lecture. So I'll just write the equation. Okay, so power is nothing but pi
P into
square
omega. Okay, pi square.
d square L, okay, into electric loading into magnetic loading, right?
Yes.
So B into A. So B is magnetic loading, A is electric loading, which I am representing here. Okay.
Yes, sir.
Okay. Into I think number of something in, so one more term was there, isn't it?
One more term. B sigma K.
Yeah, power. This is the equation of torque actually.
T square into L into sigma. That's yes, sir.
Yeah, T square L into electric loading into magnetic loading into
Magnetic
pi square.
loading.
This is torque.
Sigma
Now
in this
power.
is nothing but A into B in electric loading into magnetic or shear stress.
Yeah, shear stress.
Yes.
Exactly. And power will be nothing but torque into a speed.
Torque into angular speed, angular velocity.
But here professor must have derived in terms of RPS, revolution per second. So that here we are representing torque into RPS. Okay. So power will be equal to now pi square d square L, electric loading, magnetic loading into RPS. Okay. Now power is given 25 horsepower, right?
Yeah.
Yeah. So power is 25 horsepower. This is equal to 25 into 0.0746 kilowatt. That will be
18.65.
18.65 kilowatt. Pi square d square L. Electric loading is given with 0.55. Magnetic loading is given with 17 kilo ampere per meter into RPS. How much is the RPS? 600 RPM. 600 divided by 60. That will be RPS.
60.
So 10 RPS.
10. Yes.
Okay, so this kilowatt term and this 10 power 3 terms we can cancel. So we can calculate d square L is equal to 18.65 divided by pi square into 0.55 into 17 into 10. So can you calculate that for me?
Yes. 17 into 10, no? Yes.
Yes.
It's a 0.02.
0.02. Okay.
Yes, sir.
So now we have to calculate D, but we also don't know the value of L. Right? L is the axial length, D is the diameter of the bore. Okay.
Yes, sir.
So bore diameter you understand, right? That is the stator inner radius, just after the air gap. For inner rotor motor, bore diameter is the where the air gap ends.
Stator inner diameter, yes.
Yes, a stator inner diameter.
Inner diameter.
So Yeah. So in the problem, one more thing has been mentioned that
The pole faces are square. That one only.
pole faces are square, just to make your magnetic loading or air gap flux density waveform in kind of a square waveform, and the ratio of pole arc to pole pitch. So entire pole is not made up of squares. There is some portion which has been restricted. So L uh, L by pole pitch. So this is the pole arc by pole pitch is mentioned as 0.67. Okay.
Mm.
So can we calculate pole pitch here?
Yes, pi d by ns.
Pi d by ns. Pi d by ns. Ns you mean by?
Ns is a number of slots.
No, actually number of pole, because pole is placed on rotor. Right. For any AC machines, generally poles are placed in rotor.
Yes.
So you are correct there, but ns rather it should be np. So number of pole. Okay.
Mm.
So tau is equal to pi d by p.
P.
Okay. So pi into d, p is 4. So now I think we can get the value of L is equal to 0.67. I am just plugging in this value to this equation, 0.67 into tau is pi d by 4. So we have brought d in terms of L.
Relation.
Right? Yeah. So d will be nothing but 4L by 0.67 pi. So d square well we have already calculated.
L equal to 0.526 into D.
0.5 in L is equal, please repeat once more. L is equal to
0.526, sir.
0.526
into D.
Into D. Okay, okay. So L is equal to 0.526D. So here we can say that dq will be this value which we derived earlier, right? 0.02.
0.02.
So dq will be
0.6 into dq equal to 0.02.
0.526. Okay, so how much will it be?
1 second. 33.62.
33.62.
1 second, I will cross verify.
Okay.
33.62 mm, sir. Correct, diameter.
33.62 mm. I think you cross check once more. It should come out to be, 0.33. You are just missing one decimal point there. So 0.33 meter.
0.3362. Okay.
Yeah, 0.33.
Correct, sir. Sorry, I'm wrong. Actually, if it is mm, that 336.26. Yeah.
Yeah.
1000. Yeah.
Yeah.
I'm sorry.
Yeah. No problem. Yeah.
Okay.
So just cross verify whenever you are solving in the exam. Okay.
Yeah.
At home there is no issue.
Mm.
So that is the diameter of the machine given the parameters, right?
Yes.
So next part is we need to calculate a stack length. So can we calculate a stack length now?
Yes, sir. We have relation, na L and D relation.
We have, yes, exactly. So L is equal to nothing but 0.526 into D. D is nothing but 0.336. So
0.176.
Exactly, 0.176 meter. Okay, so any doubt regarding diameter and stack length?
No, sir.
Okay, so here the diameter is higher than the axial length, right?
Yes.
Now the last part of the problem is how much will be armature and line current. So see the problem statement is whatever was there initially. Now we need to calculate armature current as well as line current.
Series crane motor. Ampere conductors, from there we can get, na sir, electric loading they given, no? So from this relation we can get current, no?
Or other way around, power you are given, voltage you are given, you can calculate current.
Yeah, from there also.
But do not forget to take into account the efficiency value, because this 25 HP is nothing but the rating, that is input power for this machine. Okay, generally rating is given in terms of output, but since this is a DC machine, so this will be your input.
Input power is 25 HP.
Yeah. So output power. Sorry, I'm wrong actually. Whenever this 25 HP is given,
That is
that is output power. Yeah.
okay. 25 HP output power, as well. Okay.
Yeah. So efficiency will be 25 into, actually we have calculated output power, that is 18.56. Oh,
No, sir. 25 divided by, no? Okay, output power. Okay.
input power, if you
Input power.
calculate, because see, just let me draw it. So this will be your DC voltage of DC motor. Okay. And since it is a series motor, so all the armature resistance, line resistance are connected in series
Yes.
with armature. So this V and IA will be your input power. That's why we are interested into input power, right?
Yes.
In motor, what is the input? The electrical power. Output is mechanical power. So this is a DC series motor. So that is why input is electrical power. And
Output
output,
efficiency.
yeah. So output, whatever will come out here, EB into IA, that will be mechanical power. Or you can say electromagnetic power before the mechanical losses. So if you reduce the mechanical losses, so EB into IA, output power will be electromagnetic minus mechanical losses. Okay.
Okay.
So output power we knew, efficiency we are given with. So input power will be 18.65 divided by efficiency is
0.82.
0.82. So that will come out to be
22.74.
22.74
kilowatts.
kilowatt. We have calculated input power. Can we calculate armature current? Usually it is a line current, but same current is going into armature. So that's why in DC series motor, IL is equal to IL. P input divided by voltage. Voltage is 500 volt.
$45.48.
45.48 amps. Exactly, that is correct. And the same line current will be equal to armature current. So both the values will be same. Yeah.
Same.
Any doubt here?
No, sir.
Great. So let's move on. So this is the sixth problem, right?
Yes.
So we have to design an alternator, and it is desired that a number of poles to be 4, and it is a three-phase double layer winding. Which of the following number of slots is not desirable for the design? So double layer winding, what do you mean by double layer winding?
Sir, the question is not visible here. The earlier solution is actually it is there on
Okay,
the
okay, okay. Let me
screen.
refresh it. Now I think it's visible.
No, yes. In the design process, already design three phase and two layer winding, double layer winding. Yes.
So what do you mean by double layer winding?
Slot contain two coils. No, sir. This side one coil,
Exactly.
this side one
Right,
coil.
right. So in a slot there will be two coils.
Two
Single layer
coils.
winding, generally one coil
Only
will be
one
there.
coil.
Yeah. So which of the following number of slots is not desirable for the design?
32.
32. Could you please explain behind the reason?
Sir, actually, three phase in this sense, it must be multiples of three. No, 3 fours are 12.
Okay.
And 3 1 పన్నా మూడు ఒకట్ల మూడు మూడు ఆరు 16 threes are 48, but 32 is not the multiple of 3, so how it will be possible?
Yeah. So for it will be slot per pole is 8, and if you have three phase, so SPP slot per pole is 8 by 3. So the reason behind is that either it could be integer or fraction, but this is 3 by 8 is irrational number, right?
Yes, it's not.
So that's another reason. Let's say you had like whole pole and six slots in the option. So whether six slot is a feasible design for this four pole and three phase or not?
So whenever it coming three phase at the time, so this last slot is there only we can known as we know now 332 is not allowed.
Yeah,
Yes.
because here all the options are not appropriate. But let's suppose in the option you are given with six slots. Then
6
what can you say?
again.
So SPP
Hmm.
6 by 4 into 3. So it is 0.5, which is 1 by 2.
1
So
by
1
2.
by 2 is a rational number, right? So this could be a feasible design. So 6 slot is completely fine for this three phase, four pole winding. Okay.
Okay.
So you either might have heard the term fractional slot concentrated winding, or you will hear in the future lectures. So that is what fractional slot concentrated winding. So your SPP is in fraction,
Fraction.
but it should be a rational number. In the first case, 32 by 4, it is not a rational number, right? So that is why we have to discard this. Okay, so I hope that is clear to you guys,
Yes.
right? Now moving on to the next problem. Here, I hope you are able to see the problem, right?
Yeah, I can see, sir.
Yeah. So please read it and figure out what is the way to solve this.
The specific electric loading is 18,000 and average flux density is 0.46 power per meter square. The
Right.
output coefficient of DC machine is dash T ampere per
So
meter.
that is ampere turns per meter.
Ampere turn per meter. Coefficient of DC machine. Tesla into ampere. So electric loading into magnetic loading, no sir?
Exactly.
So 18,000 into 0.46. 8280 ampere turn
8
per
ampere turns per meter.
meter.
Okay. Let's see this.
Yes.
So output coefficient is nothing but electric loading into magnetic loading into pi square. If you multiply d square L into that, so that will be torque. Torque will be C naught into d square L. Power will be RPS into C naught into d square L. Okay. So here output coefficient is being asked, right? So that is nothing but BA into pi square.
BA into pi square. So I have to multiply with pi square also. 8280
Yes,
into pi square.
into
So it's
18.
81,720.32.
Okay. 0.46. So that will be, how much did you say?
81,720, sir.
720 ampere turns per meter.
Yes, ampere turn per minute.
Okay. Yeah, so that's correct.
Yes.
So that much is the output coefficient of this DC machine. Okay, I hope it is clear to you guys, right?
Yes, sir, clear.
So moving on to the next problem. A 4-pole 37 kilowatt 230 volt 1400 rpm shunt motor efficiency is given. Pole faces are again square and ratio of polar to pole pitch is given. Air gap flux density, magnetic loading and electric loading is given. We need to calculate the bore diameter of the stator. So this problem seems to be done earlier, but again we'll go ahead just to clear out our concepts. We have done the same problem for series motor, right? If you
Yes, sir.
remember.
Earlier we did actually, yeah.
Yeah.
Pi
So
square will do easily.
Sir, for armature drop in a DC machine?
yes.
Yes. So for that, can you guide us how to solve that type of
Okay.
questions?
Okay. So since there are no resistance values are given, so you won't need in this particular problem. But again, here output power you can calculate. Output power is given. Input power you can calculate from efficiency value. So let's see. So this is your input, right?
Hmm.
And your armature will be here. And this armature resistance is also in series with armature. So this is RA, this is EB, back EMF and armature resistance, right? Now, since this is a shunt motor, so your field winding will be parallel to armature.
Okay.
So this is your field winding. So this will be IL, this will be IF, and this will be I. So for shunt motor, IL is equal to IF plus IL. So you can apply KVL and KCL, you can calculate all the drops, but here no resistance values are given, so that won't be required for this particular problem. Okay, so the first thing that you should go ahead with, a power is equal to output coefficient into d square L into a speed, right?
Hmm.
Since you are
Yes.
given with power value 37 kilowatt, that will be C naught into d square L into RPS. C naught will be equal to pi square, right? Electric loading into magnetic loading. So pi square into electric loading is 22,000. Magnetic loading is 0.5. So you can calculate this value. It will come out to be pi square into 22 into
C naught equal to 1,08,565.
exactly. Okay, so that is your C naught value.
Mhm.
Now for power 108,565 d square L into RPS. How much will be RPS? 1400 RPM divided by 60.
4 by 60 we have to write. Diameter 0.298.
It will be 70 by 3.
Yes, sir.
And power is also given 37 kilowatt. So here, from here, we can calculate d square L, right? How much will be d square L?
Equal to 0.0146.
0.0146. Okay, so that should be in meter cube, I guess, right?
Meter cube, sir. Diameter square into L meter cube.
Meter cube, yeah. Now, again, we are given with a square pole face. So L by tau. So L by tau is
Equal to
given with
0.7.
0.7. Tau can we calculate?
Pi d by p.
Pi d by p.
Pi d by p.
So pi d by 4 again, right?
Yes, exactly, sir.
So L is 0.7 into pi d by 4.
4.
So
L
L
by
will come out
L equal to 0.549 d.
0.549.
9d.
Okay, that seems correct. And after that, we
Then
can calculate d. We can put this value of L in terms of d in d square L. So d square L is 0.0146. Okay, and it could be equal to 0.549 d cube.
yes, sir.
So d will be cube root of
0.29. 549. Yes.
so how much will it be?
0.298.
0.298.
Yes.
Excellent meter. So now we can calculate the value of L, that is 0.549 into 0.298. So it will come out to be lesser than that.
0.163.
0.163.
163. Yes, correct.
Exactly. So that is your axial length and that is your bore diameter. Okay.
Yes.
So we have calculated stack length and bore diameter. So that's all that was asked for this question. Okay. So any doubt here?
No,
So,
sir.
yeah, one thing I guess you are not clear with equivalent circuit of DC motors like self-excited, separately excited series motor, right? So whether I'm not sure whether that has been covered in the lectures or not by now. But if it is covered, then well and good. Otherwise, we can discuss that in a separate lecture. Please remind me for that. We can cover that in half an hour. Okay. We can take some problems to solve, so that way it can clear out. Or in the end, if today also we get some time, we can go ahead with that. Okay, so that's all.
Answer, there is a peripheral speed if it is given.
Yes,
Yeah,
yes.
so in that I have a one doubt for that equation which we have to use for this. Say for example, maximum flux density is given. So
Yes.
average that is okay. We can find out. So in that case, we require a form factor, or it means the number of poles is given, the rating is given, speed is
Uh-huh.
given.
Hmm.
Yeah, and we have to find out the total air gap flux. Say for example,
Uh-huh.
okay. Huh. So which equation is correlate this peripheral speed?
Peripheral speed and flux density, there are not any direct relation between them because
Okay.
in air gap flux density or magnetic loading, what matters is how have you distributed your magnet or field winding, right? So
Hmm.
even in torque equation, which is a factor of magnetic loading, so in torque there will not be any speed. So there is no relation. I don't know from where you are getting this question. So is that the question in current week's assignment?
So that is related to the assignment number 3.
Okay, let me see that. Which question you are referring? Just let
The
me see
question
one.
number 4.
Okay. Yeah, so here I can see. So to calculate total air gap flux, I don't think you will require peripheral speed, but on the other
Yes.
hand, to get
Yeah.
get the value of torque, because you are given the value of power.
Hmm.
So to get the value of torque, for that purpose you need peripheral speed.
Hmm. Hmm. Hmm.
And peripheral speed is nothing but R into omega. So the
Hmm.
rotor radius into a speed. V is
Hmm.
equal to R omega, right?
Yes, sir.
Yeah.
So in this particular question, there is no need of this peripheral speed, na?
So there will be need to calculate torque, not directly for
Totally.
air gap flux.
Yes,
Yeah.
yes.
Air gap flux you can calculate derive from the torques with output coefficient and d square L if that is required. So in third part, you are being asked output coefficient of the machine. So there you will get the output coefficient, right? And
Hmm.
after that, you will be able to calculate this, right? I hope you got the idea. And L by D is also given.
Yes, sir.
Okay, so that should not be a problem since we have solved two similar problems today. So I don't think that will create any issue. But still, just think over it. You will get it. It is very straightforward question, the same as we have solved already a couple of questions.
Okay, sir.
Okay,
Okay, sir.
yeah. So now let's go over 10th problem. So diameter and length of machine is given. 500 kilowatt rating, 200 volt, 1000 RPM is given. So yeah, this problem is also similar to that. So you will get the idea. Okay. So please pay attention here. So what you need to calculate is total flux.
Sir,
Right? So pay attention to the question and try to
the question is
think.
not earlier thing is
Oh,
only we can see.
okay. Sorry about that. I think now is it visible?
Yes, yes. Now we can see.
Okay. So diameter and length of the machine are given. Power is given. Voltage is given. RPM is given. All right. So maximum flux density in the air gap. So it is not electric magnetic loading anymore. It is maximum flux density.
For the EMF, we have to use the equation.
For the EMF, you can use also, but for flux, you can use in terms of form factor if you have gone through the lecture. So, what
Yeah.
is the total flux here? we are being asked total flux, right?
Hmm.
Total flux will be equal to form factor
Into
into
BAV.
B into uh, what do we call one volume of that, right? So pi
Yeah.
circumferential volume. So pi d L.
Yeah.
Or air gap area. So you air gap area per pole, because the flux will be corresponding to one pole only, right? One flux loop is completing one loop in one pole pair. So that is why pi d into L. So air gap is the length. So the area, as I discussed in the transformer course section also, what used to happen? So this is the length, right? Apart from this length, whatever the dimension is left, that will correspond to area. So this width into axial length. So again, width here is how much? Pi d. And if you have, multiple poles, so let's suppose here number of poles are not given, right? So we can assume that there is one pole pair only if no information of pole pair is given. If you have multiple pole pair, then you will have P by 2. Just that, width of the flux. So let me show you. So this is a cross section of the machine, right?
Hmm.
And flux is going out and coming in this way. So the width will be this much. And axial length is axial length. That is same, right? Axial length will not change. So what is this length? That is circumference of one pole pitch divided by number of, oh, no, not only circumference of one pole pitch. If you are calculating, so pi d is nothing but the circumference of entire pole, right? Entire core of the
Yes.
pi d is
2 pi r, or
4
you can say pi d. Yes, sir.
Total is
yeah.
two circumferences.
And if you have pole number is equal to 2, so this width pole pitch
Pi d by 2.
will also be equal to pi d. If you have p is equal to 4, then this width will be pi d by 2. Okay. So that is nothing but pi d divided by p by 2. So that is nothing but p by 2 is nothing but pole pair.
Okay.
Is it clear or do you have any doubt?
Yes, sir. Clear.
Okay. So now I think we can solve this, right? So how much will be total flux?
So here number of poles,
Number
I
of poles
will
are
pick
not
one.
given, so you
one.
can take one pole pair.
Okay.
One pole pair, not one pole pair should
One
be
pole.
appropriate.
So P by T equal to 1.
Yeah.
One 1.127, sir.
1.127 Weber.
Webers.
Yeah. So that's all about all the problems. I think you will be able to solve. Only you will face some issue in circuitry problems. So I'll just take an example of that problem so that you will get the idea behind it.
Hmm.
Okay, so I hope you are able to see the slides. So let us start with separately excited machine. So in separately excited machine, what do we mean by that? So your field is placed separately from your armature current or output or whatever the power circuit. So this is the field voltage. This is the field resistance. So you can change this field flux or field current by changing this field voltage or connecting one variable resistance in series. So you can adjust this value. So R adjusted I am writing here. So you can adjust the value of this resistance and you can manipulate the field current. And this field current is only creating the field flux, right? So you know the characteristics of flux and current. So this is nothing but IF. This is IA. And how will your power circuit will look like? So this is your armature, okay, and it is rotating. So this is DC voltage to supply. This is EB back EMF. This is RA. Okay, so this is how this separately excited does look like. Okay. Now, if you solve the KVL, so VDC will be equal to EB plus IA. So this current is equal to line current, and that is equal to armature current. So IA into R. Okay, and VF is nothing but IF into RF. Okay, so any doubt about this? We will solve one problem based on this separately excited motor. Let me take one example problem.
Please, sir.
So this is one problem I have got. Okay. Yeah. So I hope you can see the problem here. So the DC shunt motor is reconnected. Okay. So now it is reconnected as what can you see from the circuit figure? What can you see? Which type of connection is it?
Separately excited one.
Separately excited. Exactly. Okay. So this is a separately excited. Field voltage is given, right? Armature voltage is written that it can vary from 120 to 240 volt. Okay. Now we have to calculate no load speed of this separately excited motor when this R adjusted is equal to 175 ohm. Okay. So what can we do here? So when R adjusted is equal to 175, so total IF we can calculate 240 V field divided by 75 is the field resistance plus 175 is the R adjusted. Okay, so that will be equal to IF. So how much is this? It will come out to be 0.96 amps. Okay. Now we are given with one characteristics like that EF varies with IF. So with corresponding to this IF, there will be some EF or EA will be generated. Okay. So that value is given that this value of 0.96 ampere is providing the generated voltage or armature voltage that is equal to 277 volt. Okay. So we have a curve, we have an internal characteristics. Let me also bring that. Okay, so this is the characteristics. So with field current, how much is the internal voltage there? So we have calculated 0.96. So for 0.96 ampere, the corresponding voltage will come out to be 277 volt. So somewhere here, right? So that is why I was saying that it is generating EA of 277 volt. Is it clear? Are you able to see the screen?
So we have to check the graph now, sir, for that?
Yeah, so graph, are you able to see?
Yeah, not now. It is
Previously, yeah.
Okay, think a little bit lag is there. Yeah, so here you can
Yes.
see graph, right? So
Yeah,
0.96
we can see
correspond
here.
to close to 288. So now we have got from the internal characteristics the value of EA. Now it is being asked the no load speed of the separately excited machine with VA is equal to 120 volt. And in second case, VA is equal to 180 volt. And in third case, VA is equal to 240 volt. VA is this armature supply, sorry, DC machine supply voltage. So now you have to apply the KCL and KVL here. So see, this from this graph, you can see that the speed of the machine at rated is 1200 RPM, right? Here it is mentioned. Okay. And other thing is that we are talking about no load speed, right? So at no load, which current will be zero?
Yes, sir.
This IL will be zero, right?
Mhm.
So whatever
Yes.
EA, that will be equal to VA at no load. Okay. So at 277 volt, this speed is 1200 RPM. Now, for the case of 120 volt, how much will be this value? So E1 by E2 is equal to N1 by N2. So E1 was 277, E2 is now 120 volt. A speed was corresponding to 277 was 1200 RPM. Now corresponding to 120 volt, we have to calculate. So that we can calculate N2 will be equal to 120 divided by 277 into 1200. So that will be the speed corresponding to 120 volt.
Five 519.85, so 590,
590.85.
519.85.
So that much will be RPM. So correspondingly, how this circuit varies with the your field or adjusted resistance. So that's how it depends, right? So that is the problem based on separately excited. So let's suppose this was related to separately excited. Now for series motor, what happened? Any doubt regarding separately excited or from that problem also?
No, sir.
Okay, great. Now for shunt motor, what will happen, at voltage, this is supply voltage and supply current is IL. Now field is connected in sun to supply RF. Okay. And this is your armature.
This is the load.
This is RA. Okay. So load is load, if you imagine for motor side, so load is the EB into IA, that is electromagnetic power, and output power will be EB into IA minus mechanical loss. Yeah. Okay, so IL, as I mentioned, is equal to IF plus
IA.
IA. Okay. Now let's suppose you are given with RA of 0.1 ohm. Okay. And RF is equal to 220 volt. And V is also equal to 220 volt. Okay. You are given these parameters. Now you are given as input power also 1100. Okay. Yeah. You want to calculate electromagnetic power developed. Power developed will be how much? So can we calculate this value? You understood the problem, right? So see, power input is nothing but 1100 watt. So IL we can calculate from here, right? IL will be how much? 1100 divided by 220. Is nothing but power divided by V in. So it will be 5 amps, isn't it? Now once we have calculated IL, we are given with RF, isn't it? RF is 220 ohm. So how much will be IF? 220 by 220. So this voltage is parallel to RF, right? So this voltage is appearing as V. So which will be 1 ampere. You're following so far?
Yes.
Okay. And once we have calculated IF, can we calculate IA now?
Yes, sir.
So IL equal to IA plus IA.
Yeah, IL
Right.
is equal to IA plus IF. You are correct. So IA will be equal to IL minus IF, isn't it? So the
Yes,
current
sir.
coming out of the supply, the
5
portion of that will go to the field and it will create the field flux, right? And that will link to this armature. So IA will be 5 minus 1. So that will be 4 amps. Okay. So we have calculated IA. Now we just need to calculate what? Developed power. Developed power equation is IB
EBIA.
into EBIA. Exactly. So we don't know the value of EB. Can we calculate by KVL?
Yes, EB is equal to V plus, sorry, V minus
V minus
IR.
IR. Yeah. So V is 220. IA we have calculated 4 into RA is given as 0.1 ohm. So EB is nothing but 219 into 290.6.
Yes, sir.
Okay.
Yes, sir.
So power developed is EB into IA, that is 219.6. Sorry.
Into 4.
Exactly. Into 4. So it will be 878.4 watt. So that much is the developed power. Okay. So if you ignore any mechanical losses, you can also calculate efficiency. Right. So efficiency will be developed power divided by input power. So that will be 878.4 divided by 1100. So it is 79.8%. Mechanical plus frictional windage losses ignored. Okay. So I hope you got this idea of shunt motor, right? The last thing is remaining, which is series motor,
Series
which we have already solved a couple of problems, but still we will see finally. So how will be the connection of series motor? This is VDC supply. Field is connected in series with supply
the
and
armature.
armature. Okay, so this is how this connection will look like. So here IA is equal to IL is equal to IF. Okay, so all three currents are same here because all of them are connected in series. Okay, again we will take all the same parameters. So the same parameters we will try to solve. Okay. So now we can calculate developed power, right? So EB will be equal to P minus IA RF plus RA. Okay. So V is given as 220 volt minus IA, which is not provided, but we can calculate. RF and RA is given. Yeah, so other thing is
Rep 20.
for series excited motor, RF could not be such a large value as shunt motor. Okay. So let's suppose series field resistance is 1 ohm. Okay, the reason behind that also we can explain from the reasoning. So now RF plus RA is 1.1 ohm. Okay. Why RF could not be such a large value?
Due to the drop.
Drop is smallest.
Yeah, because no drop will be higher. If RF is high, it is
Drop is
connected in
more.
series. So your drop is maximum. So you are losing majority of your power in terms of losses. So whatever the power has to be reached to the output, they are dissipated in terms of field losses. So that is not desirable. And also very small RF is also not desirable because uh, low value of RF, very low value of RF, what it will create.
Critical.
Yeah, so it should not be lesser than the critical value
Yeah.
just to ensure the sufficient flux in the machine. So IF is nothing but same as IA, which is nothing but V minus EB by RA plus RF. Okay, so when RF is very small, RA itself is very small, right? RA is in the order of 0.1 to 0.2 ohm, and RF is also very small. Let's suppose ki uh, RF is also, let's suppose 0.1 ohm, and RA is also 0.1 ohm. So IF will be equal to V minus E by 0.2. So it is 5 times V minus E. So what can you see the serious issue with this equation? At zero speed, what will happen?
No load. No.
Yeah, at zero speed, this value of E will be zero,
0.
right? At 0 RPM. Why? Because E is nothing but the derivative function of speed.
Speedy.
So at zero speed, this field current or the field current is similar to line current that is going to armature, that is 5 times of supply voltage. That is nothing but 220 volt. So 1100 ampere will flow. Okay, at this condition, at starting. Though when the speed will increase, this value is going to reduce only. But at starting, this problem is there, right? This danger is there. And how much is the rated current of this machine? So rated current we will just calculate. We are given with 1100 watt as input power. VDC is 220 volt, and IA we can calculate from here. So IA is nothing but 5 ampere. But at the starting, how much is it drawing? 1100 ampere. So that is significantly higher than that. So that is the issue with series motor. That is why series motor, does not get loaded at a starting. So you rotate it at certain load or till certain speed, and then you load the machine. Right? Any doubt regarding this concept? Yeah, so this statement you will hear quite often, that why DC series motor is not loaded at starting. So that's the answer of this. Okay, so now let us move ahead with the calculation of developed power. So how much is the developed power? EB into IA. Have you
Yeah.
calculated EB? So EB is equal to IA, we have calculated 5 amperes, so 220 minus 5 into 1.1, so 5.5. So that will be 214.5 volt.
214.5. Oh, 214.5. IA. 1072.5.
1072.5 watt.
Right.
Right? So it has better efficiency compared to the other machine. So you can see the efficiency is nothing but 1072.5 divided by 1100. Okay, so if you calculate, it is 97.5% if mechanical losses are ignored. Okay, and this value of efficiency is highly dependent on this field resistance, how much the field resistance you are providing. It will change drastically with respect to field resistance. Okay.
Hello.
Yeah, you got this part, right?
Yes, sir.
Any other doubt related to this?
Sir, actually, I have a doubt related to the whenever there is written DC machine.
Yes.
Okay. And say, for example, 1000 kilowatt and diameter and length is given, and voltage rating is given. So we have to consider DC motor or DC generator in that case.
Okay.
Uh,
So,
say, for
uh,
example, question number 9 is there.
yes,
So
yes.
in that case, we have to find out generated mean EMF per
Yeah.
conductor.
So, in that case, you have to read the problem very carefully. Okay. So, see here, power is given, right? Power is given and voltage is given,
Yeah.
and D and L is given. Armature drop is given at full load. Now, here in this problem, see, so there are multiple regions. One thing is that you do not need to, apply the KVL or KCL in such circuit. That is why they do not specify whether that is DC motor or generator. But it will give you idea, like if you are given with output power and if you can calculate input power, right? And input power is definitely higher than the output power, and output power is electrical, right? In
Yes.
DC machine, output power is DC motor, output power is mechanical power. So, and in DC generator, output power is electrical power.
Electrical.
Yes. Yes, sir.
So, you have to identify either way, whichever is convenient for you. But from the question, I think you won't be needing those information regarding whether this motor is motor or generator. You can, I think, solve without that, information as well.
Hmm.
So you can try anything, either from the power or from the uh, information, whatever is given. Okay, so generally, if power rating is given, it means output power, and output power is electrical, it means generator.
Hmm.
That I am giving you a hint.
Yes, sir.
So I hope from 5 to 8 question that is solved, we have solved today. That should not be any issue in 5 to 8. 9 to 11, I think you can easily calculate EMF per conductor. So EMF equation you know, right? EMF equation you know. Total induced EMF in DC machine is how much?
In terms of the P5ZN,
Full Pfizer
Yeah,
in the 16
P5ZN
yeah,
upon 60.
yeah. Z phi n by 60
into P by A.
into P by A. What is A?
What is
What is A? This
A
value
is
of A.
parallel paths.
Number of
A
parallel
is
path.
parallel path. And it changes for lap and wave windings, right?
Yes,
Yes.
For lap winding, how much?
2.
A equal to
No,
Sorry, A
for
equal to
lap
P.
A
winding,
Left
equal to P. A equal to P.
P. A is equal to P.
Number of
And for
poles.
wave winding, it will be
A
2.
equal to 2.
A is equal to 2. Okay. So Z is the number of conductors. Okay. Phi is the flux,
Flux.
whatever is being established in the machine. Not flux density, it is flux, right? In Weber. Okay. N is a speed. So you can see that E is directly proportional to a speed of the machine.
Hmm.
Divided by 60 into pole divided by parallel path. So number of poles divided by parallel path. So this value will be eliminated for lap winding because P is equal to A. So for lap winding, you just go ahead with Z phi n by 60. Okay, so from here you can calculate total induced EMF, and induced EMF per conductor also you can calculate, right?
Hmm.
Flux density you are given, D square L you are given. So indirectly you are given the area, right? Air gap area is how much?
1.30 into 0.30.
Yeah, that is D into L. No, so that will not be directly D into L because it is not a transformer. We derive the area equation of this machine.
From the flux density.
Yeah, I think I have drawn somewhere. Yeah, so here you could see, right? So this is the area. Pi dl divided by p by 2. Circumference is the width. Got it?
Yes, sir.
Yeah.
So area is equal to, we have to take pi dl by
P by 2.
P by 2. Pole
Exactly.
pair. Sir,
Pole
here they
pair.
given an armature drop 5.5.
Yes. Armature drop is given at full load. So where will you need that armature drop of 5.5 volt?
Mm,
In flux, you won't be required. In EMF, you anyway don't require. The number of conductors connected in series.
That I don't.
So that in that also you won't be
You
required.
don't want.
so that was a confusing key where we have to use armature.
Okay. Yeah, think over it. Uh, okay. So any other doubt?
So sir, actually we don't require an armature drop in this case.
Yeah. So see. Yeah. Go ahead.
That's what, sir. What she's telling, that's right. No, for EMF, we don't want any voltage drop here, armature drop.
Yes. Yes.
Total flux generated already. We have the formula pi dl by that one. It is also not included any drop here.
Yes. Yes.
And coming to
So
last conductor series means, of course, it's number, like that is number.
if you have total number of conductors in the
Mm.
EMF equation, right?
Z,
If you
yes.
yeah, so if you have calculated Z there, now
Mm.
it only depends on the lap or wave winding.
Yes,
So
sir.
in
So
in
that is
wave
the number
winding,
of
yeah,
divided by path. You can.
yeah. So divided by 2 you can do. If it is I think the number of poles are not mentioned.
Yes,
Yes.
sir.
So I think you can straight away consider the value is equal to 2. So you can divide the number of conductors into 2 parts, and I think you can proceed.
So parallel path equal to 2.
So here, sir, we have to consider wave winding, or because if we consider lap winding, then PP will be cancelled out.
Yeah, in wave winding it will be cancelled out. In lap winding also, if the number of pole is not mentioned, then you have
Then
to assume a one pole pair, right? And in one pole pair, total number of poles is equal to 2.
2.
So A by P will also get cancelled.
So B equal to 2.
And if also the type of machine is not provided in the problem, whether it has not been specified that whether the machine is series motor, shunt motor, separately excited motor, none of the information is provided. Then what will you consider? Which machine? If none of the information related to machine type is provided in the problem, then by default you have to select separately
DC machine.
excited. Separately
Suppose.
excited. Yeah. This is all the DC machine, but you have to consider separately excited, right? And from the separately excited, you are given with this input or output. I don't know. This 400 volt is of course DC supply, right? So DC supply is input 400 volt is given to you. 1000 kilowatt is given to you as output power or developed power, that you have to figure it out. If it is a generator, then you have to consider 1000
Input.
kilowatt of output power.
1000 kilowatt output.
Then you see where you can relate with armature drop. So armature drop will be nothing but 5.5, that value of armature drop can be incorporated in the difference between input voltage and induced EMF, that back EMF, armature voltage.
That is IR, na? Armature
That is
drop.
IARA, exactly. So the difference between EB and VA or EB and VDC is given for you in the problem, right? And why that is given? Because number of conductors are not mentioned in the problem. So you have to do bit analysis on over
Okay,
that
so I
problem.
think we have to consider EB is equal to, I think, P5 Zn upon 60. From the armature drop, we can find out the EB.
I think so. I think so. There can be something, but I cannot reveal completely here.
Yes, sir.
Right?
Okay.
Yeah. So that kind of thinking you have to do over this problem.
Sure, sir.
We can discuss once the assignment due is completed. I think it is
Yes.
due on 12th. So in next week we can discuss over this problem. We will see how did you do it. Right? We will go through the solution of this problem.
Okay, sir.
Okay.
Okay.
Okay. Thank you, sir.
Okay. And any final doubt before concluding the session?
No, sir.
Okay. So that's all from my side for this week. Okay. Hope to see you next week.
Yes.
Thank you very much for joining the session. Keep tuning. Bye bye.
Thank you,
Thank you,
sir.
sir.
Bye bye.
Thank you. Bye.